Okay. So now that we are very familiar with conic sections, we can talk about solving nonlinear systems of equations. Systems of equations and inequalities have been topics that we've talked about throughout the course. So way back in sections 1.5 and 1.6, we talked about solving systems like this. We had systems of 3 equations with 3 unknowns as well. We also talked about systems of linear inequalities. But what we want to do in this section that's a little different is talk about nonlinear systems, right? So we want to talk about systems like this, right? Where the equations in the system are nonlinear. And the reason that I waited to cover this topic until we had done conic sections is because a lot of the equations that we're going to talk about are conic sections. So if you want to get a graphical understanding of what's going on, then you need to know how to graph conic sections. So, but let's get to it. Let's solve these systems. In other words, algebraically, there's not going to be anything new in this section. It's just when we go to verify our solutions by graphing that we're going to need to know how to graph conic sections. So let's see if we can solve this thing. So you're welcome to use either substitution or elimination / addition, just as you did for linear systems. In this case, so you could use either, but in this case I think substitution is probably going to be easier since I already have y solved for. So I know that y equals, well, then on the other hand, though, if I use substitution, I'm going to replace y with x squared minus 3. Then I'm going to have to do x squared minus 3 squared, and I'm going to get an x to the 4th. I mean, I know how to handle that, right? We know how to handle that now because we've dealt with polynomials a lot way back in chapter 4. But I wonder if there's an easier... There are other ways to do it. But you know what? I'm just going to go with my first sort of gut instinct and use substitution. So I'm going to plug the top equation into the bottom one and get x squared plus y squared equals 9, right? So what is this now? This is going to be x squared plus x to the 4th minus 6x squared plus 9 equals 9. Okay. And let's combine our like terms. So I've got x to the 4th and negative 5x squared equals 0 when I move the 9 over. Oh, this isn't bad, as it turns out. This is just x squared times x squared minus 5. Okay, so what do I get? I get, x equals 0, or sorry, x squared equals 0, or x squared minus 5 equals 0. And that means that x equals 0 or x equals plus or minus root 5. Now, remember, I'm solving a system here. So I need to know the y coordinates that go along with these x coordinates. So you're not done just when you get your x coordinates. You need to know the y coordinates as well. So if x equals 0, what y coordinate corresponds to that? Well, you can use either of these equations to find the y coordinate that corresponds to it. I'm going to use the top one. I think it's a little easier. So if x equals 0, then I get y equals 0 squared minus 3, so y equals negative 3. Right, so one of my solutions is the point 0, negative 3. If x equals square root 5, then I get y equals root 5 squared minus 3. That's 5 minus 3, which is 2. So I get the point root 5, 2 as another solution. And then if x is negative root 5, I think I'm also going to get 2, right? Because I'm going to do negative root 5 squared minus 3. Yeah, that's still going to be 2. So I get negative root 5, 2. So those are the solutions to the system. You should put your solutions in a solution set. So your solution set is going to be made up of the ordered pairs 0, negative 3, root 5, 2, and negative root 5, 2. Okay, so there are the solutions to the system. Now let's verify that this is correct by graphing. Okay, so remember the solution to a system should be the point or points where the individual graphs intersect. So let's see if these two graphs really do intersect at these 3 points. So I'm going to graph y equals x squared minus 3. That's just a parabola. It's been shifted down 3 units, right? Opens up. 4, 5, 6, 7, 8, 9. Okay. All right, so there's y equals x squared minus 3. And now x squared plus y squared equals 9. That's a circle centered at 0, 0 with radius 3. All right, so it's centered at 0, 0 and the radius is 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, so yeah, so definitely the curves intersect at the point 0, negative 3, right? So that solution makes complete sense. But then they do also intersect at 2 more places, right? There and there. So this should be the point, so this is the point 0, negative 3. This should be the point negative root 5, 2. And this should be the point positive root 5, 2. Okay, and that makes sense. Root 5 is a little bit more than 2, right? So we have 1, 2, and some change, and then up 2. Negative 1, 2, and some change, and then up 2. So yeah, it seems to work out, okay? So there you go. Let's do another nonlinear system. How many of these examples do I have? We've got 3 more examples. Okay, and then we'll talk about inequalities. Okay, x squared plus y squared equals 25 and x plus 2y equals 10. Same thing. I think I'm going to solve by substitution. I think I'm going to take the bottom equation and solve it for x, right? So I know that x should be 10 minus 2y, or negative 2y plus 10, however you prefer to write it down. But now I'm going to take this expression and I'm going to substitute it for x in the top equation. So I'm going to say x squared plus y squared equals 25. And now I can solve for y. So if I square this thing, I get 100 minus 40y plus 4y squared plus y squared equals 25. So rewriting this in descending order and combining my like terms, I'm going to have 5y squared minus 40y. 25 minus, or 100 minus 25 is plus 75, right, equals 0. I think I can factor out of 5. I know I can factor out of 5, right? This is going to be y squared minus 8y plus, well, how many times does this go in? 5, so once, and then 2, bring down the 5, so 15 times. Oh, that shouldn't have been so difficult. And I think I can factor this, right? This looks like it's going to be y minus 5 times y minus 3. So I get y equals 5 or y equals 3. Very good. Y equals 5 or y equals 3. Well, so if y equals 5, now what are the x values that go along with that? I'm going to plug this into the bottom equation. I'm going to say if y equals 5, then x plus 2 times 5 needs to equal 10. That means x plus 10 has to equal 10, and that means x has to be 0. Okay, so 0, 5. If y equals 3, then x plus 2 times 3 needs to equal 10. That means x plus 6 needs to equal 10. That means x needs to be 4. So 4, 3. Okay, so my solution set looks like it's going to be made up of the points 0, 5 and 4, 3. Let's verify this by graphing. So the top equation is a circle centered at 0, 0 with radius 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we can connect the dots. I should use a compass or something to get nice, perfect circles. Although that one wasn't terrible. Okay, and then the bottom equation. Well, so this is a straight line. If I solve it for y, I would get 2y equals negative x plus 10. So that would mean that y is negative 1/2 x plus 5. All right, so my y-intercept is 5. Right there. And then I'm going to go down 1 over 2. Down 1 over 2. Down 1 over 2. So 1, 2, 3, 4, 1, 2, 3. Yeah, 4, 3. I'm guessing that this circle is actually supposed to pass through that point. But anyway, this is the down 1 over 2. So this is the line that we get. So there's the top equation. So sure enough, right, these things are crossing at the point 0, 5, and at the point, well, if you make this point big enough, if you draw your circle perfect enough, right, then it's also crossing at the point 4, 3. Okay, so that makes sense, right? That's lining up for sure. Let's do another one. Ooh, this is interesting. Looks like we've got an ellipse and a circle. So you could have 4 solutions, or maybe just 2, or maybe just 1. I don't think you could have 3 solutions. Yeah, you could. You could have 3 solutions. So you could have. You could also have no solutions. So you could have anywhere between 0 and 4 solutions to this system. Okay, let's see. I'm going to solve this one by elimination. I think if I multiply the bottom equation by negative 16, I can get the x squareds to cancel. So I've got 16x squared plus 25y squared equals 400. In the denominator now it's going to be negative 16x squared minus 16y squared equals whatever 16 times 16 is. 256. Negative 256. I feel like I should have known that somehow. Okay, 25 minus 16 is 9. 400 minus 256. 144. Okay, so y squared is 144 divided by 9, I feel like is 16. Yep, 16. And take the square root, that means y is plus or minus 4. Okay, so that's not terrible. I need to figure out what x values go with these y values. So if y is equal to 4, what would x have to be? I think I'm going to plug this into the bottom equation because that's going to be easier for me. So x squared plus 4 squared equals 16. That means x squared plus 16 would have to equal 16. Okay, that means x squared is 0, so x is 0. So 0, 4 is one solution. If y equals negative 4, oh, I think I'm going to get the same exact situation, right? Plus negative 4 squared equals 16. So that would mean x squared would have to be 0, x would have to be 0. Okay, so 0, negative 4. So it looks like I'm getting 2 solutions here on this particular system. We could have had anywhere between 0 and 4, I guess. But these are the 2 solutions. Let's graph the thing to see what's going on. So x squared plus, I'm going to do the bottom equation first just because it's a little easier. X squared plus y squared equals 16 is a circle centered at 0, 0 with radius 4. 1, 2, 3, 4. 4. 1, 2, 3, 4. And 4. Okay, so there's the circle. The top equation is an ellipse. In order to get it in standard form, we need to, or in graphing form, we need to divide through by 400. So let me see. If I divide through by 400, 16 over 400 is 1/25. So this is going to be x squared over 25 plus, oh, it should be y squared over 16, right? Equals 1. So it's an ellipse centered at 0, 0 with m5 and n4. So centered at 0, 0, m is 5. 1, 2, 3, 4, 5. 5. N is 4. 4 and 4. So that's weird because to me it seems like we're going to end up with 4 solutions, and I only found 2 of them. So I may have made a mistake somewhere. It wouldn't be the first time, right? Boy, am I doing this right? So let's see. 16 divided by 400 is 1/25. 25 divided by 400 is, 1/16. Okay, yeah. All right. So the ellipse that we're getting looks like this. Oh, it is only 2 solutions. I was stressing out for no reason. Because the ellipse is completely on the outside of the circle until you actually hit this point, right? And same thing when you come back around, it's completely on the outside until you hit that point. So yeah, so those are the only 2 solutions. Oh shoot, you couldn't see what I was saying. I was saying the ellipse completely envelops the circle. So the only place where they intersect is there and there. Which, yeah, is the 2 solutions that we got, 0, 4, 0, -4. Okay, that makes me feel a little bit better. A lot better, actually. Okay, so I did find the right 2 solutions. Okay, that's that one. One more of these. Ooh, with a hyperbola this time. Looks like we've got a hyperbola and a circle. This one is already set up for us to solve by addition, though. We can go ahead and add this up. We get 2x squared equals 25. Too bad I didn't make it 50. Then we could divide by 2 and just get x squared equals 25, which would have been nice. The way it stands, we're going to have x squared equals 25 halves, which is kind of nasty. And then we get x equals plus or minus 5 over root 2. Or if you like, you can rationalize 5 root 2 over 2. I need to figure out what y values correspond to those. So if x equals, I'm just going to leave it 5 over root 2 for the purposes of plugging stuff in. I think that's going to be a little easier. And then which equation do I plug it into? I don't think it matters. They're equally easy. So I'll plug it into the top. We get 5 over root 2 squared minus y squared equals 16. That means 25 halves minus y squared equals 16. 16 minus 25 halves, 7 halves. What is going on? So, okay, sorry. 25 halves. 16 minus 25 halves is, 7 halves. Okay, so we're going to get y squared equals -7 halves. That means that we get no solution here. I mean, our solution set would be, y would be I times, root 14 over 2. Or I guess root 14 over 2i. But anyway, plus or minus root 14 over I. But this is not a real solution, so it's not going to show up. It's not going to show up in our plane down here. I mean, they're still solutions nonetheless. So I guess I'll still list them as solutions. If I let x be negative, root 5 over 2, I think I end up with exactly the same scenario, right? Because after I square this thing, it's going to be positive anyway. So yeah, or this doesn't need a root 5. Sorry, this is negative 5 over root 2. So this should just be 5. But anyway, you're going to get the same thing. Y equals plus or minus root 14 over 2i. Very, very interesting. Okay, so our solution set, I guess, would be made up of ordered pairs, but the entries themselves are not. So right here, by the way, I have two solutions. I get 5 root 2 over 2, comma, root 14 over 2i. That's one solution. And then the other solution is 5 root 2 over 2, negative root 14 over 2i. And then here I get two more solutions with the 5 root 2 negative. So cutting to the chase, I guess, my solution set would look like this. It would be 5 root 2 over 2, root 14 over 2i, 5 root 2 over 2, negative root 14 over 2i. I'm going to run out of space. Shoot. Well, that's okay. Negative 5 root 2 over 2, root 14 over 2i, and negative 5 root 2 over 2, negative root 14 over 2i. So there's the solution set. But notice that none of the solutions are real. None of the solution sets are made of real ordered pairs. So what that tells me is that when I graph this, the graphs should not intersect anywhere in the real axis system. Well, let's see. The top equation, as we said, was a hyperbola. If I divide through by 16, then I see that it's centered at 0, 0, and m and n are both 4. So centered at 0, 0, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and make a box out of this. Draw the diagonals of the box. And those are the asymptotes for the hyperbola. This hyperbola opens left and right. Okay, so it opens like that, and like that, like that, and like that. Now the bottom equation is a circle centered at 0, 0 with radius 3. So it's centered at 0, 0 has radius 3. So there's the circle. And sure enough, right, the two graphs don't ever intersect. They don't ever intersect. So yeah, no solution. I guess if I were asking you for the solution set over the real numbers, so you could say no real solutions. Right, no real solutions. So that would be that. So it's not that there's no solution to the system, it's just that the solutions aren't real. So you can say no real solutions. Okay, so that's that one. I have a little bit more to say. Like here's another system of nonlinear equations. Let's solve this system. Excuse me. Sorry, let's solve the system. You don't have to graph it. These things are hyperbolas as well, but they're kind of complicated to graph because you have to do a rotation of axes and stuff. So we're not going to graph them, but we can solve the system anyway. I'm going to solve this one by elimination. I think I can multiply the top one by. I can eliminate the 1 over y's by multiplying the top one by 2 and the bottom one by 5. So that's what I'm going to do. You might have made a different choice, and that's okay. But I'm going to do 2 times the top and 5 times the bottom. That's going to give me 4 over x plus 10 over y equals negative 10. and 15 over x minus 10 over y equals whatever 5 times 17 is, 85, negative 85. And I can add these up. I'm going to get 19 over x, the y's will cancel, and this equals negative 95. So I solve for x, right? 19 equals negative 95x, divide by 95, and x is 19 over 95 is 1/5. So x is negative 1/5. Okay? And then I can use that to solve for y, right? If I know that x is negative 1/5, then I can plug that back into the top equation and say I have 2 over negative 1/5 plus 5 over y equals negative 5. 2 over negative 1/5, 2 divided by negative 1/5 is the same as 2 times negative 5. It's just negative 10. Add 10 to both sides. And then you get 5 equals 5y, so y equals 1. So there you go. You get the point, negative 1/5, 1, as your one and only solution. Okay. Here's why we're interested in solving nonlinear systems. It says, I mean, this isn't the only reason, but the reason we're interested in doing this is because, generally speaking, it's useful, right? It could come up in various scenarios. Here's one of them. A rectangular room has a perimeter of 40 feet and an area of 91 square feet. Find its dimensions. Okay, it's a rectangular room. The area, I don't know why I drew the rectangle, but the area is 91 square feet. The perimeter is 40 feet. So maybe I can say this. Maybe I can say, let's call the width of the rectangle x and the length of it y. We know that the area is x times y, and the perimeter we know is 2x plus 2y, right? It's this plus this plus this plus this, so that's x plus y, or 2x plus 2y. And there you go. That's a nonlinear system, right? You get the system xy equals 91 and 2x plus 2y equals 40. I would solve this system by substitution. I think I can solve let's solve the bottom equation for x or for y. It doesn't really matter. I'm going to say 2y equals 40 minus 2x. So y equals 20 minus x. I can take that now and plug it in for y in the top equation. So I can say x times y equals 91. Oh, what? This is going to be so nasty. We get negative x squared plus 20x minus 91 equals 0. I can at least divide through by a negative and get x squared minus 20x plus 91 equals 0. I don't think I can factor that. Maybe I can, but I don't know. Is 91 prime? I think 91 might be a prime number, so I'm not convinced that I can factor this. So I'm just going to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4 times a times c. Well, they are real solutions anyway. Over 2a. 400 minus 364. No way. We could have factored this. How does 91... I guess 91 isn't prime. But we'll see. All will be revealed shortly. So I'm going to get x is 20 plus or minus... This is 36, right? Square root of 36 is 6 divided by 2. 20 plus 6 is 26. Divided by 2 is 13. So x is 13, or x is 20 minus 6 is 14. Divided by 2 is 7. That's interesting. So 7 times 13 is 91, huh? 7 times 13 is 91. There you go. That's the problem, is that I don't know my 13s. I don't know my times tables for 13. But yeah, 91. 13 times 7. It's very interesting. But there you go. So 13 times 7. Or 13 and 7 are two solutions for x. Now, that is interesting that we're getting two different answers for x. I wonder what we get for y. So plugging this into one of these equations to solve for y, I'll plug it into the top one. So 13. So if x equals 13, then we get. So if x equals 13, then we get x times y equals 91. That means y would have to be 7. If, on the other hand, x is 7, then we get 7 times y equals 91, and y would have to be 13. Oh, that's why we're getting those two solutions, right? So if the width is 13, then the length has to be 7. If the width is 7, then the length has to be 13, right? But it's really the same scenario. So I'm going to say, find its dimensions. We're going to say length is 7 feet. Width is 13 feet. And that's that. Let's look at another application problem. I think this one is a projectile motion thing. So it says a rock is thrown upward from ground level with an initial velocity of 100 feet per second. At the same instant, another rock is dropped from a helicopter that's hovering 300 feet above ground. I mean, why? Whatever. Okay. So another rock is dropped from a helicopter hovering 300 feet above ground. At what time will the two objects be at the same height? And what is the height? I don't even know if this is going to be like a system, strictly speaking. I mean, we could force it to be a system, I guess, but what I want to do is come up with the height function for each of the rocks. So for the first rock, it's thrown from ground level with an initial velocity of 100 feet per second. So that function is going to be negative 16t squared plus 100t plus 0, right? And the height of the other rock is going to be negative 16t squared. It's dropped from the helicopter. It says that it's dropped from the helicopter. It's not thrown, so the initial velocity is 0. But it's hovering 300 feet above ground, so its initial height is 300. And then we want to know when the rocks reach the same height. So we want h1 to equal h2, right? So we can say when is negative 16t squared plus 100t equal to negative 16t squared plus 300? Well, the negative 16t squareds will cancel. So this happens when 100t equals 300. In other words, that happens when t equals 3. So at what time will the two objects be at the same height? They'll be at the same height after 3 seconds. What is the height? Well, you take 3 and plug it into one of these equations. Doesn't matter which one. So I'm going to say h1 of 3 is negative 16. It's negative 16 times t squared plus 100 times t. This would be negative 16 times 9 plus 300, 156. Okay, so they will both, or maybe I'll say this, they will meet at a height of 156 feet after 3 seconds. Okay, so there's the answer to that one. I gotta stop this to tell my kids to stop playing with the doorstop. All right, crazy kids. So one last thing that I want to say is that we can also graph systems of nonlinear inequalities. We've talked about graphing systems of inequalities in the past, linear inequalities, but we can do the same thing with nonlinear inequalities. With inequalities, just remember you have to shade somewhere, and the way you decide where to shade is to choose a test point, right, and then see if it gives you a true statement, you know. So let's practice. Let's just practice graphing this. So first of all, I'm going to graph the boundaries, which are, if I just replace the inequalities with equal signs, those are the boundaries. So this top one is a circle with centered at 0, 0 with radius 4. 1, 2, 3, 4. 4. How many of these have we graphed in this section? So many circles centered at 0, 0 with radius 4. Anyway, but we're going to graph it with a dotted line, or with a dotted curve, since the inequality is strict. Okay? It's easier for me to graph with a dotted line anyway. Well, that's still not a very good picture, but whatever. Now to figure out where to shade, we need for x squared plus y squared to be less than 16. So I have a feeling that means we're going to be shading on the inside of the circle. But just to be sure, we can plug in a test point like 0, 0, as long as it's not on the boundary. So if I plug in 0, 0, I get the statement 0 squared plus 0 squared is less than 16, and I want to know if that's true, right? Well, 0 squared plus 0 squared is indeed 0, which is less than 16. So that tells me that yes, I'm going to be shading on the inside of this circle. I'm not going to shade it yet because I have some other curves to graph first, but I just know I'm going to be shading on the inside here of that circle. This one's a parabola opening down, shifted up 4 units. So up 4 units, then it opens down. Okay. Uh, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so that would be off the chart. So it's going to look something like this. And then to figure out what side of the parabola to shade on, again, I can plug in a test point. And again, 0, 0 would work. So if I plug in 0, 0, I get the statement 0 is greater than, 0 is greater than negative 0 squared plus 4. So I get 0 is greater than 4, which is false, right? So I'm not going to shade down here where 0, 0 was. I'm going to shade on the outside of the parabola. Right? So not on the inside of the parabola, but on the outside of the parabola. So here I'm going to shade outside. That should make some intuitive sense, right? It says y is greater than the curve, so it's going to be all the stuff on the outside of the curve. And then finally, x less than 0. Well, if I just make this x equals 0, then it's a straight line. It's a vertical line at 0. And I know x less than 0 means I'm going to be shading to the left. So I'm shading inside the circle, outside the parabola, left of this straight line. So the place where those three things overlap is right here. In fact, this last equation doesn't even do anything. Because if I shaded inside the circle but outside the parabola, I would be shading this region anyway. So this last condition doesn't even add any new information. But there you go. All right. So that's how you would graph systems of nonlinear inequalities. Pretty straightforward, I think, if you know how to graph systems of linear inequalities, and if you know how to graph nonlinear equations, then we're just putting the two concepts together. Okay. So that's that.